Bleed air is used for aircraft systems such as air conditioning, pressurization, anti-icing, and water and hydraulic reservoir pressurization. In this module, we'll look at the sources of bleed air, the consumer systems of bleed air, the distribution system, and the system controls and indications and messages and alerts on the flight deck.
Both engines supply bleed air. Either engine can supply all consumer systems. On the ground, prior to engine startup, the Auxiliary Power Unit, or APU, supplies bleed. There is also a connection for a high-pressure pneumatic ground source. To allow the APU to stabilize, the opening of the APU bleed air valve is inhibited for 2 minutes from the time the APU available light illuminates.
Bleed air is used by the air conditioning and pressurization system, wing and tail anti-icing, engines 1 and 2 starting and anti-icing, and the water and hydraulic reservoirs. Bleed air flows through single-walled ducts directly to engines 1 and 2 starting and anti-icing systems, and to the manifold from which it is distributed to the other consumer systems. The manifold supplies bleed air through a single-walled duct to the tail anti-icing system. The manifold also distributes bleed air through a double-walled duct to air conditioning and pressurization, wing anti-icing, and the water and hydraulic reservoirs.
Note that engines 1 and 2
anti-icing receive bleed air from the common duct. The controls and indicators for the bleed air system are located in the air conditioning panel on the flight deck overhead panel.
The 3 push buttons allow selection of engines 1 and 2 and APU bleed air.
Bleed air pressure at the manifold is shown in the central display in pounds per square inch.
Now we shall identify and locate the components of the bleed air supply. A ground supply for bleed air can be connected to a source by a single-walled duct incorporating a check valve to prevent reverse airflow.
After starting the first engine, external air is normally removed and the second engine started using bleed air from the running engine. Note that the RPM of the running engine may have to be increased to ensure sufficient air pressure.
The APU is also connected to source 2 by a single-walled duct incorporating a bleed valve and a check valve. It is normally the APU that supplies bleed air when the aircraft is on the ground. The ground supply serves as a backup to the APU. Remember that there is an inhibit of 2 minutes from the APU available light illuminating and the APU bleed air valve opening.
Each engine supplies bleed air from the HP compressor through the 7th and 12th stage tappings. The 7th stage tappings supply bleed air during any flight condition except idling. The 12th stage tappings supply bleed air during idling or when any anti-icing system is switched on. On the ground, the engine starting system uses bleed air supplied by the APU or the ground supply. Once the engine is running and RPM is at minimum takeoff, it takes over supply of the bleed air from the APU. The engine anti-icing systems use bleed air. The tail anti-icing system uses bleed air ducted through the manifold. The hydraulic and water reservoirs are pressurized by bleed air which they receive through the double-walled duct forward of the manifold. Each wing can be de-iced by bleed air. The air conditioning and pressurization systems use bleed air.
The 7th stage tappings on each engine supply low-pressure bleed air during any flight condition except idling. The 12th stage tappings not only supply high-pressure bleed air during engine idling, but over a wide low RPM range of up to approximately 80% N2 and when any anti-icing system is switched on.
Single-walled ducts carry bleed air from all the sources to the manifold and from there to the tail anti-icing system. A double-walled duct carries bleed air forward from the manifold to the other consumer systems. The double-walled duct runs through pressurized areas and serves as additional protection in the event of an inner duct leak. The manifold serves as the distribution point for bleed air. Check valves in each bleed air source prevent the reverse flow of bleed air into the source, which could cause damage. The high-pressure bleed valves in the 12th stage tappings open when the engines are idling or when there is a requirement for additional bleed air from any anti-icing system. The APU bleed valve is open during ground operation only and is closed automatically on liftoff.
In each source, a pressure regulating and shut-off valve, or PRSO valve, is located downstream of the 7th and 12th stage tapping junction. These valves control downstream pressure to 55 plus or minus 5 psi when engine pressure becomes excessive.
The overpressure and shut-off valves, or OPSO valves, located on either side of the manifold, open when there is bleed air pressure. They limit downstream pressure to 70 plus or minus 2.5 psi if a failure of the PRSO valve causes excessive duct pressure. The starter valves can be opened to allow bleed air into the starter motors for engine starting. The shut-off and regulating valve for engine anti-icing can be opened during icing conditions. This will be dealt with in the appropriate module. The shut-off and modulating valves for wing and tail anti-icing can be opened to allow hot bleed air into the wing and tail leading-edge compartments during icing conditions. The cabin and flight deck pack valves allow bleed air into the air conditioning packs. Bleed air 1 and 2 push buttons are located in the lower left and lower right corners of the air conditioning panel on the overhead panel. In normal operation, they are blank. The APU bleed air push button is located between the bleed 1 and 2 push buttons. In normal operation, it is blank. Operation of APU bleed air is largely automatic.
Bleed air pressure measured at the manifold is shown in pounds per square inch in the center display area. The normal operating range is 15 to 49 psi.
Finally, in this section, we will identify the anti-icing push buttons. These are located on the overhead panel. They cause the high-pressure bleed valves to open partially to increase the temperature of the bleed air in the common duct to 250 plus or minus 15 degrees centigrade. Valves in the appropriate anti-icing system also open to allow bleed air into that system. We will describe how the bleed air system operates during the following stages: ground operation, idling, 80% RPM, and maximum RPM. Let's begin with ground operation. First, remember that there is an inhibit of 2 minutes from the APU available light illuminating and the APU bleed valve opening. Touch the APU start selector to switch the APU on. With the aircraft on the ground and the APU switched on, the APU supplies bleed air to the engine starters, directly to the right engine, and through the open OPSO valves to the left engine. The ground source may also be used as a backup for the APU. Touch the right engine starter valve to simulate the entry of bleed air into the starter. No, please touch the right engine starter valve. Bleed air now flows through the open starter valve to the starter motor. APU bleed air is automatically controlled and is only available when the aircraft is on the ground. When the engines are idling, the APU continues to supply bleed air as long as the air pressure it supplies is greater than the air pressure supplied through the 12-stage tappings. Touch the thrust levers to simulate higher engine RPM and note the movement of the high-pressure bleed valves on each engine. At increased engine RPM, 12th-stage air pressure has also increased. It is now greater than APU air pressure, and the APU check valves prevent engine bleed air from entering the APU. On liftoff, the APU valve is automatically closed by the ground flight switches, thus preventing any APU air supply in flight. When the engine RPM exceeds 80%, the high-pressure bleed valves close and the 7th-stage air becomes available to the system. Touch the thrust levers again to increase engine RPM further and note the movement of the high-pressure bleed valves. Engine RPM has increased and the high-pressure bleed valves have closed. The PRSO valves control downstream pressure to 55 plus or minus 5 psi. The OPSO valves control downstream pressure to 70 plus or minus 2.5 psi in the event of a PRSO valve malfunction. Within normal operations, let us finally look at how the anti-icing system uses bleed air. Pressing any anti-icing push button activates the temperature modulating function of the high-pressure bleed valves and opens them until the temperature of the 7th and 12th stage air in the supply duct to the manifold reaches 250 plus or minus 15 degrees centigrade. Icing conditions are detected by an ice detector and cause the ice light to illuminate. In the event of icing, a message appears on the left-hand MFDU. There is no procedure on the right-hand MFDU. We will begin by considering an APU bleed fault on the ground. When the aircraft is on the ground, an APU bleed fault causes a Level 1 alert with a message in the left-hand MFDU and a fault indicated in the push button. There is no procedure in the right-hand MFDU. The procedure is stated in the Quick Reference Handbook. The APU bleed push button should be switched off and on, and if the alert persists, APU bleed air should be switched off. In this case, the APU is on, but APU bleed air is not available. Touch the APU bleed push button to select it to off. Pressing the button causes the off message to appear on the push button and the message to disappear from the MFDU. APU bleed air is no longer available. The push button should now be pressed again to switch it on, and if the fault persists, it should be switched off. Touch the push button again. In this case, resetting the APU bleed push button has rectified the fault. However, as we mentioned earlier, if the fault persists, APU bleed air should be switched off. Let us now consider an APU bleed valve failure in flight. If the APU bleed valve fails to close in flight, engine bleed air may enter the APU, possibly causing damage. This fault gives rise to a Level 2 alert, an alert message on the left-hand MFDU, and a procedure on the right-hand MFDU. APU bleed air should be switched off, and if the alert persists, the APU itself should be switched off. Now follow the procedure to rectify the fault. In this case, the fault has not been rectified and the alert persists. Since the fault persists, the APU should be switched off. Touch the APU selector to switch it off. The APU is now switched off. APU shutdown is at the pilot's discretion. The module on the APU describes this matter in more detail. An APU bleed fault on the ground produces an alert when the engines are out and whilst taxiing. An APU bleed fault in flight does not produce an alert in the phases of flight indicated.
Let us now consider an overheat. When a high-pressure bleed valve fails to close, the temperature of the air in the supply duct to the manifold exceeds the preset level. This causes a level 1 alert.
In this case, bleed air should be switched off and then on again. If the fault recurs, bleed air on the affected side should be switched off. Let us see how this operates.
The overheat in source 2 causes the affected high-pressure valve and PRSO valve to close automatically. The OPSO valves remain open, allowing engine 2 anti-icing by source 2 bleed air. Remember that a single source will meet all bleed air requirements.
Now observe the PRSO and HP bleed valves closing.
Note that the OPSO valve remains open once the temperature in source 2 has returned to normal. The bleed 2 push button may be reset. Touch the bleed 2 push button twice, once to select it to off and once to select it to on again.
Now touch the bleed 2 push button again to select it to on.
The source 2 PRSO valve has opened and bleed air from source 2 has been restored. Let us consider overheating in both sources 1 and 2. Overheating in both sources causes a level 2 alert. In this case, both bleed 1 and 2 push buttons should be switched off and then on again to attempt to re-establish bleed air. If this fails, both sources should be switched off and the procedure for unpressurized flight should be followed.
If required, ram air may be used for ventilation. Ram airflow may cause a low flight deck and cabin temperature. This is discussed in more detail in the relevant module.
In this case, the high-pressure bleed valves and PRSO valves in sources 1 and 2 are closed and no bleed air is available. If a fire breaks out in either engine, pulling the appropriate fire handle closes the corresponding OPSO valves and isolates the affected source. This will be dealt with in more detail in the relevant module. The alert caused by a single source overheat is inhibited in the phases of flight indicated. The alert caused by a dual system overheat is inhibited in the phases of flight indicated.
Leaks in the single-walled duct between either engine and the manifold cause a level 1 alert. If a leak is detected, the relevant HP bleed, PRSO and OPSO valves will close automatically.
If a leak occurs in the single-walled duct, the affected source should be switched off as a backup of the automatic system, thus ensuring that the HP bleed valve and the PRSO and OPSO valves are closed in that source. Touch the bleed 1 push button to acknowledge that source 1 has been shut off. Bleed air source 1 is now isolated from source 2, which continues to function. Bleed air is no longer available for engine 1 anti-icing. Leaks in the single-walled ducts in both sources cause a level 2 alert and cause a high-pressure bleed PRSO and OPSO valves to close. In this case, both bleed 1 and 2 push buttons should be switched off and then on again to attempt to re-establish bleed air. If this fails, both sources should be switched off. The HP bleed, PRSO and OPSO valves in both sources are closed. Bleed air is no longer available for anti-icing or cabin and flight deck air conditioning. Unpressurized flight procedures should be followed. A leak in the double-walled duct does not cause an alert. Should a leak occur in the inner wall, bleed air is carried by the outer wall. The alert caused by a leak in the single-walled duct in one source is inhibited in the phases of flight shown. The alert caused by leaks in the single-walled ducts in both sources are inhibited in the phases of flight shown. This terminates our discussion of malfunctions in the bleed air system.
In this module, we saw that bleed air can be supplied by 3 sources: the engines, the APU, and a ground supply. The APU supplies bleed air for engine starting. A ground supply can be used instead of the APU. Once the engines have reached a certain RPM, they take over bleed air supply from the APU. On liftoff, the APU bleed valve is closed automatically. Bleed air consumer systems comprise wing, tail, and engine anti-icing, engine starting, air conditioning and pressurization, and water and hydraulic reservoir pressurization. APU bleed air is used to start the engines. The APU continues to supply bleed air until 12th stage bleed air comes on stream and closes the APU check valve. On takeoff, the APU bleed valve is closed. Once the engine RPM is above 80%, the 12th stage high-pressure bleed valves close, and 7th stage low-pressure bleed air is used during flight. The use of any anti-icing system will cause 12th stage bleed air to be added to the system until the temperature of the air has reached 250 plus or minus 15 degrees centigrade. Check valves located in the bleed air supply systems prevent the reverse flow of bleed air into these systems.
High-pressure bleed valves downstream of the 12th stage tapping open to supply bleed air at low RPM and when any anti-icing system is on. They close automatically when engine RPM increases. The APU bleed valve closes automatically on liftoff. APU bleed is not automatically closed when 12th stage engine bleed is available. At idle, APU bleed is higher than idle engine bleed.
The PRSO valves control downstream pressure and close in the event of an overheat or a leak in the duct between engine and manifold.
The OPSO valves limit downstream pressure in the event of a PRSO valve failure and close when there is a leak in the single-walled duct. A fire in either engine will also cause the corresponding OPSO valve to close when the engine fire handle is pulled for the affected engine. The OPSO valves remain open in the event of overheating in either system to allow engine anti-icing from the other source. The starter valves open to allow APU or ground supply bleed into the engine starters. Starting is also possible using cross-bleed from the other engine.
The shut-off and regulating valves open to allow bleed air into the engine nacelles for anti-icing. The shut-off and modulating valves open and close to allow bleed air into the wing and tail leading-edge compartments.
Bleed air supply to the packs is controlled by the pack valves.
The controls are located in the air conditioning panel on the overhead panel. In normal operation, the push buttons are blank. An APU bleed air fault when the aircraft is on the ground causes a level 1 alert. APU bleed air should be switched off and then on again. If the fault persists, APU bleed air should be switched off. An APU bleed air fault in flight causes a level 2 alert. In this case, APU bleed air should be switched off and on again. If the fault persists, the APU itself should be switched off. An overheat in either system caused by a faulty HP bleed valve closes the affected HP bleed valve and PRSO valve and gives rise to a level 1 alert. Bleed air should be switched off and then on again. If the fault persists, that system should be switched off.
An overheat in either source caused by a faulty HP bleed valve closes the affected HP bleed valve and PRSO valve and gives rise to a level 1 alert. Bleed air should be switched off, then on again. If the fault persists, that source should be switched off. A leak in the single-walled duct in one source gives rise to a level 1 alert and causes the affected HP bleed, PRSO and OPSO valves to close. In this case, engine 2 anti-icing is unavailable and the affected source must be switched off. A leak in the double-walled duct does not immediately affect system operation and does not cause an alert on the flight deck.